In this module, we will look at the properties of matter. The three-dimensional shape of molecules affects the physical and chemical properties of a substance. Have you ever wondered what is happening at the molecular level when water is in the form of ice, liquid water, or water vapor? These are the three states in which water can exist at atmospheric pressure. In this module, we will have a closer look at what causes the water, and essentially all other matter, to be in a solid state, liquid state, or gas state. We'll first look at polar bonds and a property of all elements called electronegativity. Recall that a molecule consists of atoms of one or more elements held together by covalent bonds, and covalent bonds are formed from the sharing of two electrons between non-metal atoms. In order for electrons to be shared, the electron clouds of the atoms must overlap. Here we have a hydrogen atom, and inside the hydrogen atom there is one electron. When two hydrogen atoms come together, the two electrons can be shared between the two atoms, and together it would form a covalent bond to create a hydrogen molecule. Now the question is, are the electrons in a covalent bond always shared evenly between the atoms regardless of which elements are involved in the bond? The answer is not always. Covalent bonds can be classified as one of two types. It can be described as being pure or nonpolar, where the electrons are evenly shared between the atoms. Or it can be described as being polar, where the electrons are not evenly shared between the atoms. So what do we mean by equal sharing of the electrons in a pure covalent bond? It implies that the two electrons are attracted to the protons in both nuclei, so on average, they are found halfway between the two atoms. So in this example here, the two electrons are found halfway between the two nuclei. Whereas in a polar covalent bond, the two electrons are not shared equally, and so they are not found halfway between the two atoms. The electrons are mainly located closer to one of the atoms. In this example here, the electrons are found closer to the fluorine. So as a result, this half of the bond appears to be positively charged because the electrons have shifted further away. This ends up creating a partial positive charge on this end of the molecule. We describe it as being partially positively charged because the electrons are still being shared. If the electrons were completely transferred to the fluorine, then we would have ions and full negative and positive charges. This half of the molecule appears to be negative because the electrons have shifted closer to this end, creating a partial negative charge on this end of the molecule. The ability of an atom in a molecule to attract electrons to itself in a chemical bond is called electronegativity. It is a characteristic of all elements, and there are values associated to it. The higher the value, the stronger the attraction the element would have for electrons. The general trend is that electronegativity decreases going down the column. This is because the atoms become larger due to the larger electron cloud, and so the ability for the protons in the nucleus to attract electrons diminishes, whereas the electronegativity increases going across the row. This is because there are more protons in the nucleus, and so the attraction for the electrons increases. Therefore, in the periodic table, fluorine has the highest electronegativity, and so it has the strongest attraction for electrons. In this example here, hydrogen has 1 proton, and fluorine has 9 protons in its nucleus. This would explain why the electrons in the covalent bond are pulled closer to the fluorine atom. You can think of covalent bonds as a tug-of-war for the shared electrons between the two atoms. In a nonpolar covalent bond, there is a tie in strength, which would be the electronegativity, and so the electrons are shared equally. In a polar covalent bond, one atom has a stronger pull for the electrons, which results in the unequal sharing of the electrons. In this example here, chlorine has a stronger pull than the hydrogen. Depending on the difference in electronegativity values between the atoms, the bond can be classified as nonpolar covalent or polar covalent. If the difference is 0.4 or less in the electronegativity values, the bond is considered nonpolar covalent, and so the electrons would be shared equally. If the difference is between 0.4 and 2.0, then the bond is considered polar covalent, and so electrons would be shared unequally, and you would have partial negative charge on one end of the molecule and a partial positive charge on another end of the molecule. When the electronegativity difference is large enough, such as what is seen between a metal and a nonmetal, the electron from the metal is completely transferred to the nonmetal, forming an ionic bond. And this is why we would see a full negative charge and a full positive charge in the ions. The most common elements in the human body are hydrogen, carbon, oxygen, nitrogen, and phosphorus. And so the most common bond types in biology are carbon-hydrogen, carbon-nitrogen, nitrogen-hydrogen, carbon-oxygen, phosphorus-oxygen, and oxygen to hydrogen. Since hydrogen, carbon, and phosphorus have similar electronegativities and their values are smaller than nitrogen and oxygen, the 6 bonds can be ranked in the order shown here based on bond polarity. Although carbon and hydrogen have different electronegativity values, the difference between the two is so small that the carbon-hydrogen bond can be considered nonpolar. Whereas the difference in electronegativity values between oxygen and hydrogen are large, and so the oxygen-hydrogen bond would be considered the most polar. Let's have a look now at the effect the molecular shape can have on the properties of matter. Polar bonds in diatomic molecules makes the whole molecule polar. There is an overall positive end and an overall negative end in the molecule, like a north pole and a south pole of a magnet. In this example here of hydrogen fluoride, an arrow can be drawn to indicate the polarity of the molecule. The tail shows the positive end, and the arrow points towards the negative end of the molecule. This image here represents the electron density in the hydrogen fluoride molecule. It's just another way to show the polarity of the molecule. The red color represents high electron density due to the electrons being closer to the fluorine. It's like it's the hot zone. And the blue color represents low electron density. It's the cooler zone. Just because a molecule has polar covalent bonds does not automatically make the molecule as a whole polar. For example, here we have carbon dioxide. Each of the carbon-oxygen double bonds are polar, where the shared electrons are being pulled towards the oxygen atoms. So in the tug of war for electrons between carbon and each oxygen, oxygen will win since the nucleus has more protons compared to carbon. However, the linear shape of the molecule results in the bond polarities canceling each other out. So the pull of the electrons to the left is precisely balanced by the pull of the electrons to the right. Although there is one overall area with a partial positive charge in the molecule, found here in the middle around the carbon, this cannot be said for the negative charge. There are 2 regions that have higher electron densities, here on the left, as well as here on the right. So overall, carbon dioxide is considered a non-polar molecule. Water, on the other hand, has polar oxygen-hydrogen bonds, where in the tug of war for the electrons, oxygen will have a stronger pull. Since the shape of the water molecule is bent, the pull of the electrons towards the oxygen atom in each bond do not cancel each other out. As a result, the molecule is considered polar. There is an overall positive end in the molecule around the hydrogens and an overall negative end around the oxygen. We will now look at a special type of interaction called hydrogen bonds. Now that we understand water molecules are polar, they are actually attracted to one another. The partial positive end of a water molecule is attracted to the partial negative end of a neighboring molecule. So the dashed green line here represents that attraction between a hydrogen and a neighboring oxygen. The attraction between neighboring water molecules is referred to as hydrogen bonding. It's a type of intermolecular force. The dashed green line represents a hydrogen bond. Although it is called a bond, they are not considered real chemical bonds, as they are not as strong as a covalent oxygen-hydrogen bond. Hydrogen bonding can occur among many water molecules. They are not just limited to pairs of molecules. One molecule can have multiple hydrogen bonds, forming large clusters. This water molecule here is hydrogen bonding to 3 other water molecules. We know that water can exist as a solid, liquid, or gas, which are the 3 most common states of matter. The state in which water will be in will depend on the extent of the hydrogen bonding, which in turn is dependent on temperature and pressure. Let's have a closer look at each state. We know that water freezes when temperatures are at or below 0 degrees Celsius. This is because at lower temperatures, water molecules can approach each other and arrange themselves in such a way to maximize the number of hydrogen bonds between them. This leads to water molecules being closely packed together. Here's a simulation of what is happening at lower temperatures. Notice the water molecules are constantly moving and vibrating, but their movements are slow, allowing the hydrogen bonds to form between the molecules. As the water molecules cluster together, they become more closely packed, resulting in the formation of ice. Remember that ice is a result of hydrogen bonding between the water molecules. No new molecules are formed as the pre-existing oxygen-hydrogen covalent bonds are still intact. There is no chemical change taking place, only a change in the physical state of the water. When temperatures are above 0 degrees Celsius, the water molecules can approach each other and form hydrogen bonds. However, there are less hydrogen bonds, which results in water being in a liquid state. In the same simulation, under warmer temperatures, the water molecules are moving and vibrating more, so there are less hydrogen bonds. The molecules still tend to cluster together, but they are not as closely packed compared to water in the form of ice. As long as the temperatures are approximately between 0 and 100 degrees Celsius, water will exist in the liquid state. Again, notice that the oxygen-hydrogen bonds within the water molecules are not breaking as they move around from one cluster to another. Only the hydrogen bonds between them are forming and breaking. At higher temperatures, the water molecules are moving and vibrating so much there is little to no hydrogen bonding between each other. The result is water in the gas state, which would be described as steam or water vapor. When temperatures have reached approximately 100 degrees Celsius, water boils. So here in the simulation, the temperature was adjusted to show you higher temperatures. So when water is boiling, at this point, all the hydrogen bonding is disrupted. Because there's little to no hydrogen bonds between the water molecules, water will go into the gas state. Again, notice that there is no change to the covalent oxygen-hydrogen bonds. To try out the water simulation, check out the following link. Vary the temperature and using your mouse, click and slowly drag a water molecule around to see what happens. So we've seen that hydrogen bonding can occur between molecules with oxygen-hydrogen bonds, but it can also occur between molecules that have nitrogen-hydrogen bonds. The attraction can occur between the partially negatively charged nitrogen atoms in one molecule with partially positively charged hydrogen atoms in neighboring molecules. These types of hydrogen bonding interactions are important in the structure of proteins and DNA. For example, DNA has a shape of a spiral staircase. It is described as a double helix. The distinct shape of DNA is a result of 2 strands held together through hydrogen bonding. In this example here, you can see that the dashed blue lines represents hydrogen bonding, which keeps the 2 DNA strands together. Notice in this example that the hydrogen bonded to a nitrogen atom in one strand, here is hydrogen bonding to the oxygen atom in the other strand. Hydrogen bonding is also important in the structure of proteins. Proteins are made up of building blocks called amino acids, and amino acids have this general structure, where the only difference lies in what is in the R group. When several amino acids are linked together, they create what is called a polypeptide chain, as shown here. It's described as a primary structure for proteins. The polypeptide chain can then fold to create a secondary structure, which could be described as an alpha helix, which looks like a coil, or beta sheets, which look like pleated sheets. These special shapes are created through hydrogen bonding that occurs between the hydrogen bonded to nitrogen in one amino acid to an oxygen in another amino acid. And so the hydrogen bonding is represented by the dotted blue lines. In summary, there are two types of covalent bonds, pure and polar. In pure covalent bonds, the electrons are shared equally between the two atoms, like in the hydrogen molecule. Notice that the two electrons are halfway between the two nuclei. Whereas in the polar covalent bonds, the electrons are typically found closer to one of the atoms in the bond, such as in the example here with hydrogen fluoride. Notice that the two electrons are found closer towards the fluorine atom. The type of covalent bond depends on the difference in electronegativity between the two atoms involved in the bond. When the difference is high enough, the bond is considered polar. So in the tug of war for the electrons, the atom with the higher electronegativity will end up pulling the electrons closer towards itself. With polar bonds and the right three-dimensional shape, a molecule can be described as being polar. This would mean that there is an overall negative end and an overall positive end in the molecule. But those charges would only be partial and not full charges, since the molecules are made up of covalent bonds and not ionic bonds. Because water molecules are bent and the oxygen-hydrogen bonds are polar, water itself is polar, and so they are attracted to one another. Hydrogen bonding occurs between the hydrogen atom in one molecule with the oxygen in a neighboring molecule. Remember, though, that hydrogen bonds are not considered real bonds. They are not as strong as covalent bonds and can be easily disrupted with elevated temperatures. Lastly, the three most common states of matter, including water, is solid, liquid, and gas. The state of water is based on the amount of hydrogen bonding between the molecules. Interestingly, the solid state for most substances is typically the most dense state, or the heaviest state. However, water is unique in that liquid water is the most dense. It is actually heavier than ice. When water is frozen, the molecules arrange themselves in such a way to maximize the amount of hydrogen bonding, but the arrangement leads to ice being less dense than liquid water. This is why ice floats. Now we hope you understand how the polarity of bonds and the shape of a molecule can affect the properties of matter.